Valence electrons. Valence electrons are the electrons on the outside of an atom. They are the ones that are most responsible for many of the properties of an atom, how it behaves chemically and physically. It's the number of valence electrons. So for the main group elements, the valence electrons are those in the outermost principal energy level. So whatever the highest N level is, the highest floor in the hotel that's occupied, those are the valence electrons. And it turns out that this corresponds to the group number. Now, it's the group numbers that have the letters associated with them. So nitrogen is in group 5A. It has 5 valence electrons, and we'll see how that works. The other electrons, the ones below that, are called the core electrons. They're on the inside. It's the electrons on the outside that interact with other atoms and give rise to chemical and physical properties. So if we look at part of the periodic table, so there's this little seam here. That's where the transition metals split everything open, and we're ignoring them. So here's group 1A, 2A, 3A, etc. If we look at their electron configurations and just look at the highest occupied floor in the crazy hotel, the quantum hotel, that's what it was, we see that lithium has 2s1, hydrogen has 1s1, sodium has 3s1. They all have 1 electron in the highest principal energy level. This is why they have very similar chemical properties. We look over here at the noble gases. Well, let's look at these guys first. Let's look at the halogens. 2s2, 2p5. That's 7, right? Chlorine, 3s2, 3p5. Again, 7, and it's in group 7A. It's not a coincidence. Group 8A, argon has 8, neon has 8. How many does helium have? 2. What? Well, how many electrons does helium have in total? Only has 2. So this is group 8A. Everybody but helium has 8 valence electrons. Helium has 2 valence electrons. But it's a very similar situation because that first level can only hold 2 electrons. What's really important about the noble gases is the highest floor is occupied, full. The s and p orbitals are full. So write an electron configuration. For phosphorus, identify the valence electrons and the core electrons. How many electrons does phosphorus have? 15. Okay, so how do we start this out? 1s2, and what's next? 2s2, 2p6, 3s2, 3p something, right? You may have to stop and count at this point. 2, 4, and 6 is 10, and this is 12, so we need 3 in there, right? Yeah, that's right. So there's the electron configuration. Which are the valence electrons, which are the core electrons? For valence electrons, we're looking at all the electrons that have this highest principal number. So here we've got 3, that's the highest occupied level. So these are the valence electrons, VE, and the rest of them are the core electrons. The valence electrons are, I think of them as being on the outside, and the core electrons are on the inside. It's the things on the outside that interact with the other atoms. Any questions? So it turns out that all of this stuff we've been talking about is hiding on the periodic table. You don't actually have to memorize that order. It's all on the periodic table. We can divide the periodic table into blocks that represent the subshells, the sublevels, S, P, D, and F. And what we see is that the group number of a main group element is equal to the number of valence electrons for that element, and the row number for main group elements equals the highest principal quantum number for that element. So here it is. These two columns represent S block elements. Helium is also blue. Helium, for this purpose, belongs over here. But hydrogen and helium are, like I've mentioned before, baby brothers, right? They're the little tag-along who gets to break all the rules, and mom and dad just seem to ignore him. If you are an older child and wonder why the little one got away with stuff, your parents were tired and they just didn't care that much anymore, okay? You wore them out, so that's why he gets away with everything. So helium kind of belongs over here. But these are filling the S block. This is the P block. How many electrons can the P subshell hold? 6. 1, 2, 3, 4, 5, 6. This is the D block. How many electrons can the D block hold? Or the D subshell? Subshell. 10, right? Look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is F. 1, 2, 3, 4, blah, blah, blah. 14. You don't want to listen to me count. It's all in there. So you can look at the periodic table and do an electron configuration. So let's pick one. Let's see, what are we going to do later? We're going to do bismuth, so I don't want to do bismuth. Let's do bromine. So I'm going to show you how to use the periodic table to find the electron configuration for bromine. I'm just going to start up here. This is the period number. So this is filling 1s. Let's just draw helium in there because that bothers me. So here's helium. So 1s and, where's my pointer? 2. And then we go to the second level. 2s, 2, 2s. We count past here, 6. Then we have to go over here. 3s, 2. This is 3. 3p, 6. 4s, 2. Now this part, this looks to me, I better do a different color, that's going to be really confusing. This looks to me like it should go down like that, right? Like this part sunk. This is not the 4D. Because of the splitting, this is the 3D. So this D, the D block is n-1. So here we're in n equals 4, but when we come to this, 4 minus 1, this is 3D. So we go 3D, and we go all the way through that. That's 3D10. Here's the P block again. We're back to just N. So this is 4P, and we go 1, 2, 3, 4, 5. And there's the electron configuration for bromine. That's a lot easier than doing that silly chart with the arrows. Any questions? Isn't that beautiful? I think that's amazing. The more you study chemistry, the more you realize how utterly mind-bogglingly amazing that periodic table is. Writing the noble gas configuration or the inner electron configuration is even easier. If we were doing chlorine, go to the end of the row previous, write that in brackets, and then just fill in what comes after. So for chlorine, it would be neon in brackets. And after neon, there's 3s2 and then 3p5. That's not a 3. If you can learn how to see this on the periodic table, electron configurations are a piece of cake. We want to try to understand why they are. That's the whole quantum mechanics and the wave functions and all of that stuff. The end result, though, that's most important is being able to look at the periodic table and identify how many valence electrons does this have? Where are the electrons in these different levels, even if the levels don't make any more sense than my quantum hotel does. Let's use the periodic table to find the electron configuration of bismuth. So I put the periodic table on here so that we could use it. First, we have to find bismuth. He's hiding. There's bismuth down there. That was lovely. Didn't break. Dropped my stylus. Okay, so this doesn't say full electron configuration or noble gas shorthand, but we need some practice, so we're going to do the full business. So we're going to start up here. 1s2. I didn't leave myself anywhere to write the answer. 1s2, and then this is 2s2. And then over here, 2p6. And we come over here, 3s2. We continue across, 3p6. This is 4s2. What's next? Is it 4d? No, it's 3d, because that level's sunk down. 3d10. So that brings us up here to zinc. And this is 4p6. Then the next one is 5s2. What's after 5s2? 4d. 4d10. And then I ran out of room, so we'll jump around. 4d10 gets us here, so then we've got 5p6. And this is 6s2. Now things get a little bit interesting. Do you see this little break here? That's where we should take a pair of scissors and cut the periodic table open and insert this. These are the F blocks. So up to barium, we don't have to worry about them. But at this point, we do. And so this is where things get a little bit wonky, because this would be 5d1, and then what happens? Well, then we start filling the 4f's. So we're going to ignore that 5d1 because there's all of these after it. This is the F block. We have to do that one first. So the F blocks are actually n minus 2 because they're also sunk. So this is coming from right here. So it's in the 6th period. So 6 minus 2 is 4. This is the 4f. This is 5f. So the 4f is filled. That's 4f14. And then we go back up here. We'll pick this guy up and get all of these guys. So that's 5d10. And then how many 6p's do we have? 1, 2, 3. 6p3. Any questions? Read it off the periodic table. Of course, it can't just quite be that simple. There's some irregularities. We've talked about the 4s sublevel being lower than the 3d because of the splitting. The energy difference there, though, is not big. It's a small difference, and so sometimes there are some exceptions. This happens in the transition metals, and we've seen before the transition metals are much less predictable than the main group elements. So sometimes we have situations where the S level in a particular period only partially fills before that D level, or it doesn't fill at all. And this is not something that you can really predict from the periodic table. It's something that is determined experimentally, and then we try to remember. So these are some of the irregular configurations. So for chromium, what we would expect to see is 4s2 and 3d4. What we actually observe is 4s1, 3d5. I have a crazy analogy that helps me make sense of this. You've heard of Groupon, right? You go online, you get these coupons and stuff. Well, the Quantum Hotel has Groupon deals. And they may not make sense to you, but you don't care because you're going to save a little money. The situation here is that 4s room is exactly half full, and the 3d room is exactly half full. So if we draw this out, here's 4s, and the next one is 3d, and there's 5 of those. So our expected is that we've got 2 here and 4 there. But it turns out there's a deal. If you half fill both of those rooms, then you get a deal. So that guy is like, oh, well, awesome. We can save money and I can have my own bed. How cool is that? Who wouldn't do that? So there's an extra stabilization when these levels are half full. And so a lot of these come to that. So 4s2, 3d9. It's more stable if the 4s is half full and the 3d10 is completely full. Molybdenum is similar to chromium. It does the half full thing. And ruthenium and does a similar thing to, what's it doing? It's not. It's just its own random thing. That's some weird groupon deal that only ruthenium got. Palladium, by moving these up to the D, then the D is completely full and the S is empty. And there was a special on that. The electrons do this because it happens to be lower in energy. The reason that it's lower in energy has to do with the penetration and the shielding and the specifics of that particular atom, that particular element, and how its wave functions work out together. And so some of this we can come up with ideas of why to help us remember, but mostly it's just kind of random.